let's talk about gravity, real gravity, and energy and potential energy. So I want to talk about and derive the expression for the gravitational potential energy by using an example. And then I will find the generic gravitational potential energy, and then I'll do the same thing numerically in Python, because that will be fun. So let's start with the situation. Imagine that I have the Earth. That shouldn't be too hard. There's the Earth right there. And I have a 1 kilogram object, a distance from the center of the Earth, and I'm going to let it fall over here. And I want to find the change in kinetic energy. I want to know how fast it's going. And I'm going to say R1 is 3 Earth radiuses and R2 is 2 Earth radiuses for no real reason other than that I just picked that. So since we're dealing with the displacement here, we want to use the work energy principle. So this says work is the change. If I just have my system, let me put that right here, system of just, let's say it's a ball, of the ball, then the work is the change in kinetic energy. A ball can just have, if you have a system of a ball, it can only have kinetic energy. And so now what forces do work on that? And that would be this gravitational force right there. I drew it right there. So the gravitational force is in the negative x direction. Let's call this the x direction for now. It's going to be in the negative x direction going from here to there. And it has a value of g, mass of the Earth, mass, divided by the distance squared. So in that case, the problem is that this is a non-constant force. In general, I would say work is F dot delta R, but if that's not true, if the force or the displacement's not constant direction, then we can write this as the integral of from point 1 to point 2 of F dot dr. And so now we have to do an integral because our force is not constant. So we're going to integrate the work done by gravity going across this thing. And then we could use that to find the change in kinetic energy, which I honestly don't really even care about. Okay. So let's do this integral. I'm going to write down F, I'm going to write down dr, and I'm going to do it. So let me put up here F. In this particular case, it's going to be negative g, mass of the Earth, mass, over x squared times x, that's times the vector 1, 0, 0. I want to write it as a vector. Okay. And so if I'm going along the x-axis, this would work. This isn't the best form, but this would work in this case. What about dr? Well, if I'm moving in the x direction, dr is going to be a tiny little step, and we're going to write that as dx 0, 0. We're moving in the x direction, so my displacement's in the x direction, but just a tiny little bit, dx. Okay, so now we got to do the dot product. Let's do F dot dr. Now the nice thing here is that this should be a scalar value so that we can integrate. And I've chosen it so that the integral is in one dimension, so it's an easy integral. These line integrals can be complicated, but we're doing it in the easiest way possible. Okay, so here's my force. I'm going to take this dot that. So how do I do the dot product? Well, I'm going to take this term is in everything, so I can just pull it out front. Negative g, mass of the Earth, mass, over x squared, and then I'm going to get 1 times dx plus 0 times 0 plus 0 times 0, right? Because dot product, you multiply the x components together and add them to the y components multiplied together and add them to the z components multiplied together. So in the end, I get negative g, mass of the Earth, mass, and then I'll put this as dx over x squared. Now I want to integrate that. So the work done is going to be the integral from x equals r1 to x equals r2. I have an x integral now. That's what's nice of this whole thing. Negative g, mass of the Earth, mass, over x squared dx. This stuff's a constant. I'm going to pull that out front. Negative g, mass of the Earth, mass, times the integral from r1 to r2 dx over x squared. So if you remember, an integral is an antiderivative. So we're thinking about what would I take the derivative of and get that? And the answer is x to the negative 1. If I have x to the negative 1 and I reduce the power by 1, I get x to the negative 2, and that's what that is. But I need to include a negative sign in there too. So this is going to be equal to the work done by gravity is going to be equal to negative, so that negative goes away, g, mass of the Earth, mass, and then I have 1 over x from x equals r1, x equals r2. So it's going to be g, mass of the Earth, mass, over this, r2, minus I feel like I did something wrong. R2 minus R1. Oh yeah, R1. Okay, I was thinking. Okay, I got it. G M E M over R1. Or we can just write this as G M E M 1 over R2 minus 1 over R1. Now, is this positive or negative? Should it be positive or negative? Remember, if work is equal to positive, then delta kinetic energy is equal to positive. So if I go back over here, what should I expect? Well, if it's falling towards the Earth, it should increase in kinetic energy. So delta K should be positive. Also, the work should be positive because the force is in the same direction as the displacement. It's moving in the same direction. Right here, R2 is smaller. R2 is closer, so it has a smaller value than R1. So 1 over R2, this is going to be a bigger number than 1 over R1. So this whole thing is going to be positive. So it is positive work, and we can use that to calculate the change in potential energy. Let's just do it real quick. Let's just calculate the work done. And then I'm going to do it numerically, and then I'm going to come back to talk about potential energy. So if I put this in, work equals, remember my values for these things. I have gravitational constant, 6.67 times 10 to the negative 11th. And then I have the mass of the Earth, which is 5.972 times 10 to the 24th. I'm leaving off the units. My mass was 1. And then I have, these are both multiplied by the radius of the Earth. I'm going to factor that out. So let's put it over here. The radius of the Earth is 6.378. Oh, I got it. 6.378 times 10 to the 6th. And then I have 1 over R2 is going to be 1 over 2 RE, minus 1 over 3 RE. So let's put that in the calculator. Here's my calculator holder right there. Right there. On. Clear. Let's just enter these things in. Now, a tip, pro tip, or amateur tip. That's not good. I want to put that so you can see it. Well, that's fine. I'll put it right here. If you use the scientific notation button, it's going to make your life easier for this stuff. So I'm going to do that. I'm actually going to do this part. No, I'll do that last. Okay, so let's just enter this. Clear. So I'm going to say 6.67 scientific notation, negative 11, times 5.972 scientific notation, 24. And now I'm going to multiply by the stuff on the top. So times, parentheses, 1 divided by 2 minus 1 divided by 3, which I could do. I don't have to do that. I feel dumb now. Divided by 3, but I did it. And all of that divided by this, 6.378 times 10 to the 6th equals. And I get, oh, I hate when it does that. Let's see. Equals 1.04 times 10 to the 1, 2, 3, 4, 5, 6, 7 joules. Okay, how would we do this same thing numerically without integrating? Well, what we're going to do is integrate without integrating. So here's my picture. Here's R2. Here's R1. So I'm going to pick delta R is the vector. Let's pick 1,000 meters. I'm picking 1,000. So it's going to be delta R is this way, delta R. Delta R is negative 1,000 meters. So I'm going to go from here to there, and then the next step would be from here to there. another delta R, and then another delta R not drawn to scale. And I'm going to just keep moving until I get to R2. That's the first thing I'm going to do. And then at each one of these steps, I'm going to calculate F. F is negative G, mass of the Earth, mass, over, and then let's just use x squared times 1, 0, 0, right, the negative sign. So it isn't in the same direction. And then I can do F dot delta R is equal to delta work, right? That's the work done over that short little path. What I'm doing is assuming that the force is constant. It's not constant, but I'm assuming it is. And if I have a short time step, a small time step, it's fairly constant. And we can always change that. I'll actually call that dx equals 1,000, and then we can change it. And then once I calculate the work over here, I just need to move and do it again so that the total work will be the sum of the delta works. And let's see if we get the same value, right? I got this right here. Let's see if we get the same thing. Okay, so let's do this in Python. Switching to Python. Python activated. Here's Python. And I will give you the code. Let me make this bigger. Bigger. That's a little too big, but that's fine. I like big. Okay. I was just printing that to run. So there's my G, the gravitational constant, the mass of the Earth, the radius of the Earth. Let's go ahead and put R1 equals 3 times RE. R2 equals 2 times RE. That's the same thing we had before. And now I need dx is 1,000. And I'm going to put the initial x value because that's the thing I'm going to move. Let's actually call it as R. R is equal to vector R1, 0, 0. So that gives me my initial x position on the x-axis. It starts right there. Now all I'm going to do, now let's say dr is vector negative dx 0, 0. And so by doing that, I can change my step size. I don't have to worry about changing everything else. Now, all I want to do is move until I get to R2. So let's say while r dot x is greater than or equal to R2. R2 is just a scalar value, and maybe that's not the best way to do it, but I did it. So r dot x is my x component of this vector position right there. So what I'm going to do is say r equals r plus dr. So that moves my r value, right? Because dr has a negative dx value, it's going to move it. And then let's just keep doing that. And then when we finish, it'll stop. And I'll say print r equals r. And let's see if it ends up at 2re. Let's print 2re also. Print 2re equals r2. Let's run that. So it worked, right? So I ended up at the same place, about the same place. There's a little bit different because I probably overstepped that and then printed it. But it's gonna be good. It's gonna be good. Now we can calculate the work, but the first thing I'm going to do is to set the work equal to 0. I'm going to calculate the work during each step, and I need something to add it to, and that's what I'm going to add it to. So I need to start with the value. If I don't start with the value, I can't do it. So the first thing I'm going to do is to calculate the work. In order to do that, I need to calculate the gravitational field. So let's calculate that. F equals negative G times the mass of the Earth times m. I didn't put m up here. M equals 1. Times r, the norm r, that I'm going to write it as a real vector, divided by the magnitude of r squared. So that's my force. Now I have dr, which doesn't change. I have my force. I can calculate the work. D work is going to be dot f dr. And so dot product is built into Python. I don't even need to code it in there. It's already in there. Right? I can just say do the dot product of these two vectors. They're both vectors. I can take the dot product. Now I'm going to add that to my work. Work equals work plus d work. And then I'm going to move my step. And then I'm going to be done. That's it. I'm done. Let's print it out. So let's print W equals W joules. And if there's an error, I'm going to blame my calculator. I'm not going to blame this, but let's just see what happens. So let's run this. I guess I should save it. And now run it. And I get a work of 1.041 times 10 to the 7th joules. The same thing. Okay. Now, if I wanted to, if I didn't think that was a very great answer, I could go up here. I could change dx to 100 and run it. I'm going to get a better result. It's going to take longer, but I'm going to get a better result. Okay. And so that's the work done. And we can make graphs and things like that, but I don't want to make a graph. I just want to show you how to do a calculation for something like this. The nice thing about this method, it doesn't matter if I'm going in a straight line or not. I could go at an angle, I could do whatever. As long as I can describe what dr is during each step of the path, I can calculate the work and I can calculate the total work, and that's awesome. Now let's talk about potential energy, because that's really what I want to talk about. Okay, back over here. So let's say that I calculate the change in kinetic energy for the ball. I did that. Delta K ball, and it was equal to, what did I say, 1 times 10 to the 7th. About. And that was for the system of the ball. Now, let's say I have the system, and also notice that I'm assuming delta K Earth is 0. If I drop this 1 kilogram ball, the Earth's not going to move. We can deal with the moving Earth later. It's not that terribly difficult, but let's just say that it doesn't move right now. Now let's take the system of the ball plus the Earth. Ball plus Earth. In that case, I can say work is the change in kinetic energy of the ball plus a change in kinetic energy of the Earth. And in this case, if I think of this as my system, what forces are acting on the system? And the answer is none. So the work done is going to be 0. And this, we already said the Earth doesn't move, so that's 0. So this says the ball has no change in kinetic energy, which we know is not true. It shouldn't matter what we pick for our system and to see what the final speed of the ball is. It's going to be the same independent of how that ball falls. So that means that this cannot be correct. We have to have some other term in here. And in fact, we're going to write it like this. Work equals the change in kinetic of the ball plus the change in kinetic of the Earth plus change in gravitational potential energy. And that is going to be equal to 0. There's no work done, right? But if I want this equation to be the same as for the ball, which was work equals delta KB plus delta K Earth, then this W for the ball system has to be equal to the opposite of the change in potential of the change in potential energy. So if I move this to the other side, I get 0 equals delta KB plus delta KE minus work done on the ball system. And so you see here that and that have to be the same. So delta U has to be equal to negative the integral from R1 to R2 F dot dr. But I already did that integral without the negative sign in there. So I can write this as negative G mass of the Earth mass over, let's just say, should I say it X? What did I call it? Right here. I want to use the same format. I just put it just like this. So 1 over R2 minus 1 over R1. That's my change in potential. That's my change in potential. That's my change in gravitational potential. Now, one of the things that we like to do is to say, well, what if I start not from R1 is 3 Earth, but what if R1 equals infinity R radius of the Earth? Something really large. If I do that and I put in R1 is very, very large or goes to infinity, as this number goes to infinity, this term goes to 0. So now I get what I wanted, which I want to put on a new piece of paper because it's that important. I get the expression for the gravitational potential energy with respect to infinity. So I get UG is negative G, mass of the Earth, mass over just, let's just call that R. That's my gravitational potential. And I'll just put with respect to infinity. Infinity. And beyond. Beyond infinity. It's important to realize that this is useful, but when we do the work energy equation, we're always going to get a change in potential. Okay, we're always going to get a change in potential. But that's where that gravitational potential energy comes from. Hopefully that's useful.